Hey everybody, welcome back to our Materials Informatics series. Today we're going to walk through some actual Jupyter Notebook examples of what I think are some really good, well put together best practices because we wrote them ourselves. So let's dive into it. What do we mean by best practices and where does this get taught, right? So this is a new field. There's not even really good textbooks yet for this. So if you are trying to find where are the best practice explanations of how to make sure that you're doing materials informatics correctly, the best place to look are in articles like this one that we wrote. This was published in 2020 by a student that was visiting my group, Anthony Tang, as well as a couple of my researchers and some friends in the field who all had helpful things to say. So this paper, it was published in Chemistry of Materials. You can see it's been downloaded a gazillion times already, even though it's only a year out. And we think it's just because it's really valuable. In fact, one of the best things about this is not actually the article itself. It's this. It's these Jupyter notebooks that go along with it. We published these on GitHub, where you're going to be able to go notebook by notebook through all of these to figure out and show you what's the best way to do this. So let's hop over to the GitHub notebooks. Okay. So to find this, you just go to that article. I'll have the link here as well, but you have github.com/AnthonyWang/best practices. I think I'll put a link to this GitHub on mine for this class as well. This is awesome. We've really gone through this trying to comment it as well as possible to make this as easy as possible to use. You know, we even have instructions on how to get started with, Jupyter notebooks, how to create a custom environment to run this stuff is, how to create that environment and make sure that all the dependencies are there. It's all really well put together, so I encourage you to look through this. But for today, we're going to look through the notebooks, right? So I'm going to hop over here to notebooks. This overview is basically the README from this GitHub, but you could start right here if you wanted to. On 0B, if you open up this Jupyter notebook, you'll be able to see, first off, that all the libraries that you were supposed to install with the environment installed correctly, and it'll also check to see whether you can do work on a CPU or a GPU. Okay, so let's hop back. Really where we get started is right here with this data loading and cleanup. Why is this important? Well, a big part of best practices in materials informatics is being skeptical of the data and analyzing the data and cleaning up the data. We've talked in this class about the different repositories that are out there, but in practice, there's a lot of bad data in those repositories, and it's up to you as the domain expert to look through that data in the best way you can and try and clean it up. So here's an example where we've taken data from the NIST JANAF thermochemical data. So NIST, again, does a great job of measuring data really carefully for lots of different things. In this case, it's thermochemical data, heat capacity. We're going to grab that data, and then we're going to clean it. We've intentionally poisoned it. We've messed up some of the values on purpose to show you what you could be looking for. We're going to clean that data. Then we're going to split it up, and we're going to show you how you can build basic models with it. So first thing I'm going to do is I'm going to grab my different libraries that are useful. So NumPy, Pandas, Matplotlib for plotting, that sort of stuff. This really cool tool called pandas_profiling. They have this module called profile report. It's really cool. So we're going to point to where our data is. In this case, the data is this heat capacity data demo. Let's just take a look at that CIV file real quick, or the CSV file. So I have this in my Materials Informatics folder. I'm going to go to my the GitHub, and then in the GitHub I have these worked examples, and you can see all of this stuff here. So inside the best practices, here's the data, and in the data you can find the original one, right? So we're going to do the CP data demo. So this is the original data that we've gone through and made a couple duplicate entries, and we've change some of the temperatures to crazy numbers, and we haven't told you where those are at, but that's all present in this CSV file. So here's what it looks like. You have three columns. You have one that's entitled formula, this one's entitled condition, temperature in Kelvin, and this one over here is called property, heat capacity with units of joules per mole Kelvin. Right away you can see that there's things like that, like missing values, right? Again, we've gone through and added some of that. NIST didn't have that, right? They did a great job, but we've added a few things like that. And you can see that for a given formula, you have a bunch of different temperatures and different heat capacity values, right? And if you've studied heat capacity, you know that it has this general shape where it sort of approaches 3R at high temperatures. If we pull this up in Excel, yeah, sure, that's typically what it looks like. As you go from low temperatures to high, it approaches the Dulong-Petit limit of about 3R. Great. So that's what our data looks like here. So let's go ahead and close this and keep on cleaning our data in these Jupyter notebooks. So we're going to read that data in. We're going to read it into pandas, into a data frame, just because that's an easy, awesome way to work with it. And then we can take a look at it. By doing df head, you can see the first 10 entries. It's what we just basically did with the CSV. You can do this describe method. The describe method has a bunch of useful statistics in here, right? It'll tell you the total number, the average, the standard deviation. It'll tell you the minimum. For example, right here we see a minimum temperature of -2,000. What does a negative temperature mean? Is that an error? Probably, right? It shows you the quartiles where they're at, lots of things like that. A negative heat capacity, same problem, right? There's something even better though, which is this pandas profiling, right? If you run it, and I'd have to actually have this running as a Jupyter notebook, it creates this widget which has all this really cool information. If you haven't played with that before, really recommend you check it out. It's really cool. It shows you high cardinality features. So if you want, it'll tell you, one of the columns is formulas, and obviously because it repeats a bunch of those formulas in a row, it tells you that category is high cardinality. It has few entries relative to how many total entries there are in the formula, meaning it must be a category with high cardinality, right? It'll tell you how many empty cells you have, how many duplicate cells you have, how many duplicate rows there are, where they are, what their values are. It makes it really easy to look for errors and bad data. It helps you clean your data. So if you haven't checked out Profile Report from Pandas Profiling, I can't recommend it enough. Everyone should do this, right? It makes it really easy as a first pass to find crazy stuff, unrealistic temperatures, missing values. It makes it really easy to find those. Okay. Now we're going to go ahead and I think it's useful because those formulas in the CSV file had really long titles. Let's just shorten those down. So instead of condition temperature K, let's just call that T, right, for temperature. Instead of this whole thing for heat capacity, let's just call that CP, right? So one of the first things we do is we need to go through and check for empty cells, right? We know that they're there. Our Pandas profile report showed us that they were there. So now we need to get rid of them. And there's tons of ways to get rid of them in Python. In fact, if you're watching this video, you probably know Python better than I do. But here's one way to do it. In your data frame, you could make a list of Boolean values in your formula column by looking in the data frame in the formula column, right? And asking, is it null? That will return a list of trues and falses. Where it's true, that's basically saying, yeah, there's an empty cell there. So we can use that list. We're going to do the same thing, by the way, for temperature and for heat capacity. So now we have 3 lists with trues and falses in them, which tell us where it's true that there's a missing value there. Well, great. We can then use those values and we can say, come over here. We're going to go say that our data frame is equal to the initial data frame, but now we're going to drop it. We're going to drop rows. Where are we going to drop them? We're going to drop them in data frame 2 at the location of where these Boolean lists are true, at that index, dropping it horizontally, right? So if you're not familiar with Python, that's what that snippet of code essentially means. So that's going to drop the entire rows if we have a few missing values. Now, that's not the only thing you could do. In fact, a lot of times in machine learning, dropping a whole row, maybe you've got like a whole bunch of features and it's just missing one. Dropping that whole row means that you lose a lot of information that might have helped your model. So there's other things you can do. If it's not a number, if it's empty, that's going to be a problem when you try and do math with it. So you have to do something. Some options are, so you could replace, if there's a missing cell, you could just replace it with the average of what's in that column. And you could say like, well, that's going to be an error, right? You're adding error to your model. Well, you are, because you added something that was the average, and that wasn't necessarily, it was almost certainly something else, but your overall model performance might be better because you didn't drop out all the other information along that whole row. So there's this interesting balancing act between, you know that you're adding bad data technically, but you're saving lots of good data. And so overall, it might give you an improvement in your model performance. So in any case, here in this case, we had very few. There was like 8 or 9 out of 4,000. So we just dropped them. What do we have? We had 13 rows that we dropped. No big deal. Out of 4,500, just drop them. Okay. Now, there's other ways to do this, right? There's other ways to do that. Here's one where now we go through and we check for and remove unrealistic values. So on this one, we just did a simple thing again. We created a list of Boolean trues and falses anywhere where the temperature or the CP values were less than 0. Those don't make any sense. They're not physical. And so let's just scrap them. Okay, so that's what we did here. We dropped them just like before. And you know what we actually are missing in here that we need to add, it looks like we haven't added it, is we need to get rid of duplicates. You know, we got rid of empties and we got rid of unrealistic values, but we forgot to drop duplicates, unless I'm missing it somewhere. Looks like we forgot that. So that should be added to this list, and we'll go ahead and get that added soon. Okay, so we've cleaned up our data. Now that it's cleaned, we need to split it. So we've talked about the rationale behind splitting. What does the code look like? Well, first off, and I love this, we published this in a paper recently, in this one here, in this paper in IMMI, but if you just split your data 15 different times, or whatever it was, we split it 30 different times just randomly, look at the variation in the scores that you see, the metrics. We talked about R squared or MAE or MSE. Just splitting it randomly 30 different times, look at the variation. Now, which one of these do you think people report when they actually build a model? The best one, don't they? It's not very fair, is it? Splitting it a bunch of times gives you a feel for what the actual value is. The actual value is probably somewhere in the middle with some standard deviation. It gives you a feel for the confidence that the model has. So don't just report the best value. Split it a bunch of times and report how the performance varies, right? That's a much more accurate thing to do here. In any case, how do you split it, right? If you're going to do that 30 times or 10 times or whatever, how do you go about that? Well, okay, here we go. Same things as before, except this time we're going to bring in from sklearn, which again is a terrific library made for machine learning. We're going to import train test split, and I'm going to do a random seed just so that this is reproducible, okay? So we're going to grab the data that we've cleaned. We exported this cleaned comma separated value thing after we cleaned it up and renamed some of the columns, and sure enough, it has, you know, the shape that we thought it would have. It's got the columns named just like we thought they would be. Well, what we need to do is, when you do machine learning, you always have to have your input data, right, and your target, what you're trying to predict. So you have to split those, and the convention is capital X for your input variables, lowercase y for your target variables. So we're going to split that. We're going to say inputs are the formula and the temperature, and the target variable is going to be heat capacity. So split those up, okay? Now, in sklearn, there is a built-in function, not surprisingly, for train test split, and it will randomly split your data up. If we were to do that, we're going to run into a big problem, right? The code is really simple. You know, you can get your X train, your X test, your Y train, your Y test, all by just doing this test train split, sending it your X and Y that we just defined. The problem is that it's going to do it randomly. Why is that a problem? Well, remember what our data looked like, right? It was a bunch of values of the same formula. So what's going to happen? Let's say 20% of those are going to get put randomly in your test set. So it's going to keep most of these for boron oxide, but one or two of them from a different temperature is going to get put in your test set. So the first time that my student built this model on heat capacity data, he came and met with me and he's like, holy crap, we have a model that's like R squared of 99. And I was like, sweet, this is so great. But immediately we were like, wait a minute. That's too good. There's no way it's that good. What's wrong? And you should have the same mentality. Best practices means being very skeptical of your own work, especially when it's too good, right? So we gave it some thought, and sure enough, with some thought, we started to realize, oh, it's training off of, let's say, 9 out of 10 of these temperatures. It doesn't know 800, but it's got all the others. So then when it's predicting, we're basically telling it what the values are just above and just below it. But what we thought it was doing was that it had never seen boron oxide before at all, and it was predicting it so well. Well, that's a totally different thing. If it's predicting it when it knew the values close by it, that's like the same problem with like the clustering analysis that I showed you with LocoCV in the last video, because it was essentially these were very highly clustered. That's essentially what we have here. The only difference is the temperature, and it's just doing a tight interpolation. But what we wanted the model to do, the task that we had in mind, was any new chemistry that you give it, you know, some formula it's never seen before, aluminum oxide, if that wasn't there, right? Could it predict that? Well, no way. The performance there on that true test set is going to be way worse than this. So that was our problem. So what we had to do is we had to come up with a way where we split our data up, but we don't do it randomly. We split it in a way that if you have a formula in the test set, that same formula cannot be present in the training set, and vice versa. So how do you do that? You know, nowadays I think sklearn has like a k-folds group by, where you do k-folds separation by groups. We just did it by hand. Here's how we did it. We basically figured out how many total unique formulas there are, and there's 244 of them. And then we said, okay, well, let's split those up manually, by hand, into groups, making sure that of those 244 formulas, none of them are present in the different data sets simultaneously. So here's our 244 unique formula. We figured them out. We went through, created a set out of it, and we listed them, all the unique ones. And then we created a little block of script that will, first off, define how much goes in each set, how much goes in the validation set, how much goes in the training set, how much goes in the test set, right? And then we assigned numbers of formula of those 244 to each one in accordance to the size. And then once we knew which formulas were in each set, well, then we could go and we could one by one go through our rows and assign into these actual data frames based off of whether or not that formula was in the correct training set. So check through this code if you want, but it's a way to carefully assign things so that you don't get formulas spread across training and test. That's known as data leakage. When you leak data from your training set and it's actually present in your test set, your model's going to do artificially well, but it's not doing what you think it's doing. And so it's sort of like a form of p-hacking. You shouldn't do it. You're tricking only yourself and people who use your model into thinking that it has better performance than it really does. That doesn't help anybody. So be skeptical, clean that stuff out. So here's what we did. We took a look at now our three different training, validation, and test data sets, and sure enough, we don't see any, all the boron oxides are here, all the boron magnesium compounds are here, all the barium hydrogen, nothing's spread over into multiples. So good. Looks like we've separated it nicely. Okay. All right. So now that we've split it, awesome. Let's save those into 3 different comma separated value files, and we're ready to go on to our next step. Okay. Now that we have cleaned our data, we've split it. Now we can start to build some classic models. And for today, for these best practices video, this is as far as I'll go is in this one. But it's awesome. First thing we have to do, we haven't featurized our data yet. These are just strings of chemical formulas. Like, our machine learning model doesn't know what that means. We need to add some featurization. So we're going to do that based off of the composition-based feature vector, which you saw in a previous video how that works. So you see me doing, the regular stuff as before, but this time we're also eventually going to grab the composition-based feature vector as well. Okay. So we're going to load our data. We have to grab our training, validation, and test sets. We grab them, check their sizes. If you want to, you can do something called subsampling. In material science, we usually don't have giant data sets. It's typically really pathetically small data sets, so we don't need to shrink them to make our model training go faster, typically. But if you wanted to, then you could subsample, and there's some code to do that. Then we need to generate our features using the composition-based feature vector package. We've recently made this pip installable, so it's even easier. The code is slightly different. You saw it in our previous video, but it's even easier. Okay. So here all I'm doing is I'm renaming some of the columns because the composition-based feature vector expects the input columns to be formula and target. Okay. So here we go ahead and do that renaming. So now that they're renamed, we are able to now use our composition-based feature vector. This describes, there are a few keyword arguments. You can choose whether you want to drop duplicates automatically, whether you want to extend features to include things like a temperature column. In this case, temperature columns can be really important, so we want to extend it to include that. If you want to sum your features or not, we have some of these options available as you generate this composition-based feature vector. So you can choose what you like there, as well as what type of element properties to use when you generate them. I like the Oleanic set, but Matt Tvek and others are also pretty slick. Okay, so we generate our training, validation, and test sets by doing this featurization. Okay, and sure enough, that you get, what used to have just a chemical formula, you see that it's been transformed into 177 columns. The very last one is temperature. Everything else was created as a part of this composition-based feature vector, and it's left some of them off, but like lots. It took a single string and turned it into a long feature vector array, right? That it's going to do the math on. Okay, this is not yet scaled or normalized. It's important in machine learning to scale and normalize your data, right? Think about it. Some of the features were like really large numbers, maybe like density. Density could be up to like 20 or 30 and as low as like 0. But other ones are like the number of valence electrons, which are totally different numbers. Maybe it goes up to like 100 almost, down to 0. To make sure that these features are comparable, apples to apples, you scale and normalize them, right? So you're going to scale them down so that their average is 0. And then you're going to normalize them so that it goes between -1 to 1 for all those values. We're going to scale and normalize them. And again, what's great about this is that sklearn, the library for machine learning, it's already got built-in tools for this. It's got standard scaler and normalizer from this pre-processing module. It makes it super slick. So great. We're going to use standard scaler. You have to fit and transform to your training data, and then you just transform your validation and test set, but you don't fit those ones. You just transform them. You can read more about that in the documentation for standard scaler. Same thing with normalizing. We're going to normalize all 3 of those, okay? And at that point, we're ready. We've split our data up. We've featurized it. We're ready to start building models. And what's really slick and made it so easy is, again, that in something like sklearn, look at all these different models we can implement really easily, all from just sklearn. We've got ridge regression, support vector machine, more on that in our next video, linear support, vector machines, random forest, extra trees, adaptive boosting, gradient boosting, all these different types of algorithms for finding patterns in your data and exploiting those patterns to make predictions are at a fingertip, like they're right there. So here we are importing all of them. The dummy regressor, that's just guessing, right? I think that's just either reports the average or it just guesses. I can't remember. I think it's the average. We're importing ridge, AdaBoost, gradient, extra trees. We're just grabbing all these things. And then our metrics, again, sklearn makes it really easy to report metrics because these things are just, you can built in use them. Because we're going to test a bunch of these models at the same time, my student side, they decided to build a bunch of functions that allow us to do these one right after another. So there's functions for instantiating the model, functions for fitting the model, functions for evaluating the model, functions for fitting your evaluated model, functions for appending the results into somewhere where we're going to collect the results, all these things. It makes it easy to do that. What's missing here is hyperparameter tuning. So we need to go back and add that to show people how to do hyperparameter tuning. That's an important part of best practices that's just not here yet. And I think we'll stop here and you can follow through the rest of it yourself. But essentially we try out the models. It keeps track of how they do. It shows you, here's the different model names. Here's the model parameters that were used. These are the things that eventually we should write code for how to hyperparameter tune these things. Here's how long it took to train the model. Here's the R squared. Here's the MAE. This is all for the training set. Here it is for the validation set. Then we do the same thing but for our test set. And you can actually produce these parity plots. It's pretty slick. It makes this really easy. So I highly recommend going through these best practice documents because I think they're going to make you a better materials informatics practitioner because we've given a lot of these a lot of thought. And then last thing, we've got another module on neural networks. You can take a look at those in PyTorch, I think that's written. And then here on visualization, we've put together some really nice code for actually plotting these things. So I showed you, for example, these parity plots. We have some nice built-in ML figures, right? You can download these things and actually create these plots automatically in a way that's really easy for you, where they're beautiful. They include these histograms. All the hard work is done for you. We've got tools for making residual plots if you want to look at like the residual error or look at loss curves or even looking at elemental performance, right? Are there some elements that do better or worse in your model? You can actually visualize this in these tools that we've put together for you. We think it's good stuff. So I hope that this best practices video is helpful. So far, we've shown you how to featurize with composition and structure. We showed you some linear and nonlinear models. We've shown you metrics and some of these best practices. Let's now dive into some of these other algorithms that are out there because you clearly saw a whole bunch of them. Support vector machines, random forest, and those both have several flavors and varieties. Let's show you how some of those work in our next video. Okay, stay tuned.